Welcome all. In liquid state and solutions, today we are going to discuss about dependence of vapor pressure on intermolecular forces and also on temperature. Okay, so the first one is dependence of vapor pressure on intermolecular forces. The smaller the intermolecular forces present in a liquid, the higher the vapor pressure, because the weaker intermolecular forces will permit molecules to escape relatively easily from the liquid. So the rate at which molecules escape will thus be high, and such liquids are more volatile. Okay, so from this we can analyze that smaller the intermolecular forces, the higher will be its vapor pressure. So weaker intermolecular forces will permit the molecules in a liquid to escape freely from the liquid surface. Okay, so the rate at which molecules escape will be very high in the case of weaker intermolecular forces or smaller intermolecular forces. So such liquids will be more volatile. Okay, then let us consider the example of diethyl ether, ethanol and water. So let us consider the hydrogen bonding, intermolecular hydrogen bonding in these three liquids. In the case of water, there is extensive association through intermolecular hydrogen bonding. But in the case of ethanol, there is association through intermolecular hydrogen bonding, but not as much as in the case of water. Okay, that is ethanol is C2H5OH, and in the case of diethyl ether, that is C2H5 or C2H5, there is no hydrogen bonding. In the case of water, hydrogen bonds in ethanol are weaker than those in water. Okay, so the intermolecular forces decrease in the order water greater than ethanol greater than diethyl ether. So we know that intermolecular forces decreases with increase in temperature, increase in vapor pressure. So vapor pressure at a given temperature increases in the order water less than ethanol less than diethyl ether. Okay, so in the case of these liquids, that is diethyl ether, ethanol and water is the least volatile and diethyl ether is the most volatile. Okay, next is dependence of vapor pressure on temperature. The vapor pressure of a liquid is a constant at constant temperature. So vapor pressure does increase with increase in temperature. However, the number of molecules with higher kinetic energies is greater at the higher temperature. Okay, that is when temperature increases, we know that vapor pressure also increases. So the number of molecules with higher kinetic energy will be greater at the higher temperature. So a large fraction of molecules with sufficient kinetic energy will overcome this intermolecular forces and then escape at higher temperature. So the higher the temperature, the higher the vapor pressure of a liquid. So we have to familiar with this boiling point, normal boiling point and standard boiling point terms. When the vapor pressure becomes equal to external atmospheric pressure acting upon the surface of the liquid, it begins to boil. Okay, so a liquid begins to boil when the vapor pressure becomes equal to the external atmospheric pressure acting upon the surface of the liquid. So the first term is boiling point, the temperature at which the vapor pressure of a liquid becomes equal to the atmospheric pressure is known as its boiling point. In the case of normal boiling point, it is the temperature at which the vapor pressure of a liquid becomes equal to 1 atm pressure, and it is known as its normal boiling point. For water, it is 100 degrees Celsius or 375.15 Kelvin. The next term is standard boiling point, the temperature at which the vapor pressure of a liquid becomes equal to 1 bar pressure is known as its standard boiling point. In the case of water, it is 99.6 degrees Celsius. Okay. So, next is boiling point increases with increase in atmospheric pressure and decreases with decrease in atmospheric pressure. We can see that in the case of higher altitudes. At higher altitudes, liquids boil at temperatures lower than their normal boiling point because of the atmospheric pressure is very low in the case of higher altitudes. So in hill stations, we know that high pressure cookers are used for cooking food. This is because the liquids boil at temperatures lower than their normal boiling points at higher altitudes. Okay. The next is a figure showing variation of vapor pressure with temperature. Here we can see that vapor pressure of a liquid rises with temperature in a non-linear way. Okay, so when we analyze this behavior, there is an equation connecting the vapor pressure and Kelvin temperature. It is P and T respectively. That is Clapeyron-Clausius equation, and it is given by ln P is equal to minus delta vaporization H divided by RT plus C. Delta vaporization H is the enthalpy of vaporization, and R is the universal gas constant, and C is a constant, and T is the temperature, Kelvin temperature, and P is the vapor pressure. Delta vaporization H is the enthalpy of vaporization, that is the enthalpy change accompanying the vaporization of 1 mole of the liquid. Okay. It is expressed in joule per mole, and R is the universal gas constant, and it is seen that from the equation 1, a plot of ln P versus 1 by T would yield a straight line with a slope that is negative delta vaporization H by R. That is when we plot this ln P against 1 by T. Okay. So it will result a straight line with slope minus delta vaporization H by R. Thus, by measuring vapor pressure of a liquid at different temperatures and plotting ln P versus 1 by T, we can determine the delta vaporization H, that is enthalpy of vaporization. Okay. So here's the plot of ln P versus 1 by T for H2O, that is water and diethyl ether, C2H5 or C2H5. These two are straight lines with their slopes delta H, that is delta vaporization H, negative delta vaporization H. The next is equation 1 can be integrated to obtain the following integrated form of Clapeyron-Clausius equation, that is ln P2 by P1 equal to delta vaporization H by R into T2 minus T1 by T1 T2. When we take the natural logarithm to log, that is log P2 by P1 equal to delta vaporization H by 2.303 R into T2 minus T1 by T1 T2. Okay, so here P1 and P2 are the respective vapor pressures of the liquid at Kelvin temperatures T1 and T2, and thus by knowing the values of delta vaporization H and the vapor pressure at one temperature, the vapor pressure of the liquid at another temperature can be calculated using this equation, that is log P2 by P1 equal to delta vaporization H by 2.303 R into T2 minus T1 by T1 T2. So that's about dependence of vapor pressure on intermolecular forces and also on temperature. Thank you.